Hako Metal Industries' forging process begins with cutting round bar stock to length using an automatic cutter. The cut pieces are placed in a hopper and automatically fed into a gas furnace for heating. Heated billets are positioned in molds for hot forging or transferred by robot from an induction heater for unmanned forging. After cooling, flash is removed with a press. Shot blasting eliminates scale and lubricant. Finally, each forged part undergoes visual inspection before moving to the next stage. Genga Forging's HANOULHNFG 1350 is a high-performance forging press designed for heavy-duty industrial applications. With a maximum capacity of 1,350 tons, this hydraulic press enables precise and efficient forging of large metal components, such as flanges, gears, and shafts. The HNFG 1350 features advanced control systems for accurate force regulation and stroke control, ensuring consistent product quality and repeatability. Its robust construction and reliable hydraulics provide durability and reduced maintenance downtime. Widely used in automotive, aerospace, and energy sectors, the Genga HANOULHNFG 1350 supports complex forging processes while optimizing productivity and operational safety. The fully automated forging process begins with advanced bin picking, where a 3D scanner identifies suitable steel blanks in a bin. A robot then picks up, orients, and places each blank onto a conveyor. The blanks are transferred to an induction heater to reach the required temperature before entering the forging press, which applies 4,000 tons of force. After forging, the parts move to a trimming press with 500 tons of force to remove excess metal. The entire line, operated by 6 coordinated robots and automated equipment. Tanaris Bay City's seamless pipe manufacturing process combines advanced automation with metallurgical precision. Production begins with steel bars cut into billets of precise weight, then heated to 1250 to 1280 degrees Celsius in a natural, gas-powered rotary hearth furnace. These billets are pierced into hollow blooms using a barrel-type piercer, leveraging the Mannesmann effect. The blooms are elongated in a finishing mill, reheated via induction, and diameter reduced in a stretch-reducing mill. Heat treatment follows, reheating above austenite transformation in the austenitizing furnace, rapid quenching to form martensite, then tempering to restore ductility. Pipes are resized, straightened, then subjected to hydrostatic, electromagnetic, and ultrasonic testing. Final processes include facing, beveling, automated threading, and coupling. Pipes are drift tested, lacquered or varnished, measured, stenciled with heat and pipe IDs using Tanaris pipe tracer tech, and finally bundled. This fully integrated process ensures mechanical reliability, dimensional accuracy, and compliance with strict quality standards, maintaining Tanaris's leadership in seamless steel pipe innovation. The Danieli NA30920 rebar rolling mill is a high-performance solution for producing rebars with superior dimensional accuracy and mechanical properties. Equipped with advanced automation and precise temperature control, the mill enables continuous hot rolling of billets into rebars. It features multiple stands, a quenching and self-tempering QST system, and high-speed shears. This setup ensures efficient production, consistent product quality, and energy optimization, meeting demanding construction industry standards. Morator Steel industry uses die forging technology to produce high-quality precision forged components. The process begins by selecting suitable raw material billets, usually bars or round blocks, which are heated uniformly to the optimum forging temperature. The heating process improves The heated billets are then positioned into a pair of different precision-machined steel dies, which define the final shape of the component. Using powerful hydraulic presses, the billets are compressed inside the closed dies, causing the metal to flow and fill every cavity of the die. This creates parts of various shapes depending on the required product. These are then transported to the storage bins on the line. Die forging improves the internal grain structure by aligning the grain flow to the shape of the part, significantly improving mechanical properties such as strength, toughness, and fatigue resistance. Skilled operators carefully monitor process parameters, including temperature. After forging, components undergo controlled cooling and may be heat-treated to reduce internal stresses and optimize metallurgical properties. Morator's die forging process is widely used in the production of engine parts, automotive components, and heavy machinery, providing forged products that are reliable, durable, and high performance. At Arsan in Kirkham, the shaping of molten iron is a precise and carefully controlled process. The facility specializes in single-piece castings ranging from as small as 3 kilograms up to massive 11,000-kilogram castings, showcasing their capability to handle a wide range of industrial needs. One notable project involved the casting of a single 3-ton piece. This casting process starts with melting high-quality iron in the furnace until it reaches the proper molten state. Once the iron is fully melted and homogenized, it is carefully poured into prepared molds designed to achieve the exact shape and specifications required by the customer. The molten iron's temperature and pouring rate are strictly monitored to ensure consistent quality and to avoid defects such as porosity or cold shuts. After pouring, the casting is allowed to cool gradually, allowing the iron to solidify uniformly, which enhances the mechanical properties and structural integrity of the final product. Following solidification, the casting undergoes cleaning and finishing processes to remove any excess material or surface imperfections. These may include shot blasting, grinding, or machining, depending on the customer's specifications. Arsan's expertise in producing large, single-piece iron castings up to 11,000 kilograms demonstrates their advanced foundry technology and commitment to quality. Their ability to handle heavy and complex castings makes them a trusted supplier for industries requiring robust and reliable metal components. This combination of technical skill and modern equipment ensures that each casting meets stringent standards for dimensional accuracy, strength, and durability. The 12,500-ton hot forging press line is engineered for high-volume production of precision metal components under extreme pressure and temperature. The process begins with heating steel billets in induction furnaces to approximately 1,200 degrees Celsius, ensuring optimal plasticity for forging. Once heated, billets are automatically transferred to a descaling unit to remove oxide layers, followed by precise positioning in the die area using robotic manipulators. The heart of the system is the 12,500-ton hydraulic or mechanical press, capable of exerting massive compressive force to shape the hot metal within closed dies. This allows for the forming of complex geometries with superior grain flow, enhancing mechanical properties and structural integrity. The tooling includes upper and lower dies with precise tolerances and integrated cooling systems to manage thermal expansion. The unloading process of non-modulated steel front axles must ensure material integrity and operational safety. After heated forging and preliminary processing, the front axle is transported to the unloading station via rollers or chains. During operation, it is necessary to avoid collisions between the journal and the support area to prevent damage to the surface hardness or geometry. The entire process is usually controlled by a PLC system to ensure the subsequent process. At Morator Steel Industry, the forging process begins by heating round bar stock to forging temperature. The material is then shaped using large hydraulic presses for free forging, applying controlled force to form engine components and other parts. Skilled artisans perform manual finishing to refine dimensions and surface quality. This combined process ensures precise geometry, improved mechanical properties, and consistent quality in heavy industrial forged products. Morator Kogyo's large hydraulic free forging press enables powerful shaping of metal billets. Skilled artisans use this advanced press to manually transform square billets into precise round shapes through controlled forging. This combination of cutting-edge hydraulic technology and traditional craftsmanship ensures high-quality, durable forged products with excellent dimensional accuracy. REVL, Rain Engine Valve Limited, Plant 2 in Medchal, Hyderabad, operates a comprehensive production line for high-precision engine valve manufacturing. The process begins at the raw material store, where cut bars are prepared for pre-machining. Initial operations include upsetting and forging using a press, followed by solutionizing heat treatment. Specialized joining processes such as friction welding and button welding are conducted, with deflashing performed post-weld. In the machining phase, valve heads are turned and faced, followed by copy turning and seat grinding. Additional operations include centerless grinding, chrome plating, and seat induction hardening. Advanced processes like plasma transferred arc welding enhance surface integrity. Each valve undergoes a leak test, dimensional checks with multi-gauges, and magnetic particle inspection (MPI) for surface defects. The standards room/QA lab ensures quality with tools like micro-hardness testers, profile projectors, roundness testers, and contour recorders. Final steps include finishing and packing, where valves are laser-marked, oiled for corrosion protection, and securely packed. REVL's integrated workflow ensures precision, durability, and performance in engine valve manufacturing. The M30GMI LLTurn offers complete machining capabilities for complex workpieces. combining the functionalities of a high-precision lathe, a full 5-axis machining center, and optionally a gear cutting or deep-hole drilling machine. With a swing diameter of up to 520 mm and a maximum machining length of 1,800 mm, this multifunctional turning milling center is ideal for producing both shaft-type and chuck-type components with high accuracy and repeatability. Its robust design and advanced control systems allow seamless transitions between turning, milling, drilling, and contouring operations, significantly reducing setup times and minimizing workpiece handling. In the machining of a demonstration crankshaft, the M30G efficiently handles a 550 mm long, 150 mm diameter blank through multiple integrated operations. The process includes rough turning, milling of crank contours, axial and radial drilling, and precision finishing, all completed in one setup. This not only ensures consistent part quality, but also optimizes cycle time and productivity, with the ability to integrate live tooling, automatic tool changers, and modular clamping systems. The M30G/MILLTURN provides a flexible, all-in-one solution for complex part geometries, commonly found in aerospace, automotive, and energy sectors. It exemplifies modern complete machining by combining precision, versatility, and operational efficiency in a single high-performance platform. The Okuma MUL-TUSB 550 is a high-performance, multi-function turning center, equipped with a 240 degrees B-axis milling head, dual spindles, and a 5,000 revolutions per minute H1 spindle with CAPTOC8 tooling. Supporting up to 160 tools via ATC, it allows complete part machining in a single setup. Controlled by OSPP with collision avoidance system, it ensures precise, efficient machining without re-zeroing thanks to Okuma Absolute encoders. The M20G/MILLTURN is a compact, high-rigidity machining center featuring a motor spindle concept for multi-process capability. It enables precise six-sided machining with a counter spindle and supports gear skeeving. Dual B-axis systems allow simultaneous B-axis turning, enhancing flexibility and reducing machining cycle times. The Okuma Multus U3000 multifunction turning center features a tilting B-axis head and dual spindles, enabling advanced operations such as power skiving for gear production. With a machining diameter of up to 650 mm and length of 1,500 mm, it supports complex turning and milling. The B-axis swivels from -30 degrees to 210 degrees, and the HSKA63, or CAPTOC6, milling spindle reaches 12,000 revolutions per minute. The machine performs internal/external turning, contour milling, E4 to 29 mm drilling, deburring, and engraving on spherical surfaces. Thanks to the OSPP 300SA control and 40-tool magazine, expandable to 120, the Multus U3000 ensures high flexibility, precision, and complete machining in a single setup. The Okuma MUL-TUSB 252 integrates turning and milling with a 225 degrees B-axis and a 12,000 revolutions per minute CAPTOC6H1 spindle for complete machining on a single setup. Using Mastercam simulation, users can verify toolpaths, collision check, and optimize machine movements on the B252. Featuring 40-tool ATC, optional 60, 0.001 degrees B-axis resolution, compound Y-axis motion, and full contouring C-axis, it offers precision and versatility. Thermo-friendly construction ensures stable performance, while optional automation via ARMROID enhances productivity. The OSPP 500 control simplifies operation with intuitive graphics for both novices and experts. The 1/1 helmet project by Daishin Seiki demonstrates high-precision 5-axis CNC machining using a 120 kg billet of A7N01T6 aluminum reduced to a 3.6 kg finished part. DMGMORI machines combined with HyperMill CAM software-enabled precise toolpath programming, advanced collision avoidance, and efficient multi-axis strategies. HyperMill's custom algorithms supported accurate surface finishing and optimized roughing operations. High spindle speeds, fine tool selection, and adaptive machining paths ensured exceptional dimensional control and surface quality. This technical achievement reflects the potential of modern 5-axis machining and CAM integration in producing complex, lightweight components for industries such as aerospace, motorsport, and precision engineering. The Mr. 290 milling head have robust cutting-edge geometry ensures high stability and strength, making it well suited for corner milling, face milling, roughing, and finishing operations. The tool delivers extended tool life and high material removal rates, supported by optimal cooling through both liquid and air supply, which enhances process reliability. Typical machining parameters for the Mr. 290 include a cutting speed of up to 260 meters per minute, depth of cut ranging from 2.5 to 25 millimeters, and variable width of cut from 5 to 50 millimeters. Feed per tooth values vary between 0.1 and 0.15 millimeters, with feed rates up to 1,740 millimeters per minute, enabling efficient and precise material removal while maintaining surface quality. Milling with the corner and face mills from Tool Factory Cutting Tool Solutions GmbH utilizes high-performance carbide substrates combined with advanced coatings. Their indexable inserts and tool holders are designed to maximize material removal rates and tool life across a wide range of machining tasks. The product range includes inserts for fine finishing, roughing, and medium machining, compatible with all common tool holders. Typical applications include face milling with depths of cut AP of 3.5 millimeters and widths of cut AE up to 41 millimeters. Fine face milling at 0.5 millimeters AP, rough and finish contour milling, helix milling with a 35 millimeters diameter and 1 millimeter pitch, as well as pocket machining and slot milling with various cutting parameters. The laser cutting machine, equipped with the Precitech ProCutter 2.0 head, enables precise sheet metal cutting up to 20 millimeters thick, ensuring high accuracy, clean edges, and efficient processing for industrial-grade steel fabrication. Kirkham Motorsports University presents the machining of a custom-forged billet aluminum 427 FE engine block. Starting from a massive 386-pound solid aluminum block, specially forged for precision and strength, the process transforms it into a highly detailed and lightweight engine block, weighing approximately 64 pounds after machining. The initial step involves CNC machining the bell housing side of the block using a multi-axis machine, followed by flipping the block to machine the water pump or front side. Precision is maintained by securing the block onto different fixture plates for each machining operation. To tackle complex geometries, the block is mounted on a 4th-axis rotary table, allowing multi-directional machining. Custom end mills were required due to the block's intricate vertical walls, prompting on-site grinding and modification of cubic boron nitride, CBN, end mills for optimal clearance and cutting performance. Key features include machining for dart and cast iron wet sleeves, which improve cooling efficiency similar to modern Formula One engines. The cylinder holes are carefully drilled and necked down for O-ring seals, enhancing reliability. Throughout the process, it demonstrates advanced CNC techniques and in-house tooling solutions, showcasing the blend of traditional forging and modern precision manufacturing to create a high-performance, lightweight engine block. Dart billet blocks and heads are precision crafted from single pieces of billet aluminum. Starting from a 500 lb billet, they machine it down to a 150 lb big block, capable of producing over 3,000 horsepower for pro-modified race cars. Using advanced CAD design, Dart collaborates with engine builders to tailor blocks with features like tall decks, wide bore spacing, and revised lifter angles. The billet aluminum undergoes a drawing process to align grain structure for maximum strength. After rough machining, heat treatment hardens the metal, followed by meticulous quality control including CMM inspection. Blocks are lined and bore-honed for iron sleeve installation, create unique engines optimized for peak performance. The machining of a V8 engine block, specifically probing, boring, and surfacing, is a critical process ensuring engine performance, durability, and reliability. Utilizing the Rolex F79A, a floor-to-floor machine renowned for precision and rigidity, operators can execute these tasks with exceptional accuracy and repeatability. Initially, the block undergoes probing to establish exact reference points and verify dimensional accuracy. The Rolex F79A employs advanced probe systems to capture the block's geometry, allowing the CNC controller to adjust machining paths and compensate for casting variances. This ensures that subsequent operations align precisely with the original specifications. Following probing, boring is performed to machine the cylinder bores to final diameter and geometry. The Rolex F79A's heavy-duty boring heads, combined with precision tooling, provide consistent bore diameter, roundness, and taper control. The machine's rigid structure minimizes vibration and deflection during cutting, resulting in superior surface finish and long-term durability of the cylinder walls. Finally, surfacing the deck face of the V8 block is executed on the same machine. The F79A's large table and robust spindle allow for uniform material removal, restoring flatness and parallelism critical for proper head gasket sealing and combustion chamber integrity. The surfacing process includes coolant management and chip evacuation systems to maintain optimal cutting conditions and extend tool life. Overall, the floor-to-floor capability of the Rolex F79A streamlines the V8 block machining process, reducing setup times and enhancing quality control through integrated probing, boring, and surfacing in one machine cycle. Electropolishing stainless steel is an electrochemical finishing process that removes a thin layer of material from the metal surface using direct current in a temperature-controlled electrolyte bath, typically a mixture of sulfuric and phosphoric acids. Parts are positively charged, causing the removal of surface material, including embedded impurities and free iron, improving corrosion resistance and producing a bright, smooth, and passivated finish. The process can be controlled with extreme precision, down to 0.0002 inches, and is especially effective for medical, semiconductor, and food-grade applications. Electropolishing also reduces raw surface roughness by 10 to 30%, improves cleanability, and enhances the chromium oxide layer, exceeding the corrosion protection of nitric or citric acid passivation. It is compliant with ASTM B912, A967, and A380 standards. Kranic Ball Bearings Factory specializes in the production of a wide range of rolling bearings, including tapered roller bearings, cylindrical roller bearings, and spherical roller bearings. The factory also manufactures bearing elements, grinding spindles, repair kits, instrumentation, tools, machines, equipment, and machine components. Comprehensive design and construction documentation support all manufacturing processes. The production process begins with rigorous quality control of raw materials, followed by forging and annealing to achieve optimal metal properties. Turning and washing prepare components for heat treatment, which enhances hardness and durability. The factory produces cages and rollers with precision, then performs grinding to ensure exact dimensions and surface finish. Assembly follows, integrating all components into finished bearings. Each bearing undergoes marking, thorough final product inspection, and quality verification to meet strict industry standards. Finished products are carefully packed and stored under controlled conditions to preserve quality before shipment. Kranic's integrated approach, from design through manufacturing to quality control, ensures reliable, high-performance bearings for diverse industrial applications worldwide. A perfect product starts with perfect material. They produce their bearings using steel from renowned global suppliers. Each steel batch delivered to the factory undergoes thorough analysis. As one of the few bearing manufacturers with its own metal inspection laboratory, this ensures a stable manufacturing process and guarantees our products consistently meet the highest quality standards. High-quality rail bolts from AGICO Group are manufactured to meet stringent railway standards, ensuring safety and durability in rail fastening applications. Track bolts are designed to securely fasten rail ends at joints, with sizes varying based on the rail section requirements. Proper diameter and length are determined according to applicable standards to guarantee optimal performance. The manufacturing process involves using certified raw materials subjected to heat treatment and surface protection to enhance strength and corrosion resistance. Bolts undergo precision forging and threading to achieve exact dimensions and mechanical properties. Quality control includes rigorous inspections and testing to ensure compliance with specifications. Types of rail bolts produced include button-head oval neck bolts, diamond neck bolts, fish bolts with rail nuts and spring washers, clip bolts, clamp bolts for Russian standards, anchor bolts, T-bolts, and special custom bolts. Installation guidelines mandate proper torque application, alternating bolt placement on rail sides, use of ARIMA spring washers, and lubrication of threads and joint surfaces. These practices ensure track integrity and operational safety under heavy loads and harsh conditions. Rolex Rings Limited specializes in manufacturing hot-rolled, forged, and machined bearing rings, utilizing 22 forging lines with a combined installed capacity of 144,750 MTPA. The company operates 508 machining spindles, capable of producing 66 million parts annually. Core processes include high-speed hot forming, heat treatment, cold rolling, and precision die making. The facility supports extensive automation to optimize cycle times and reduce manual intervention. Products range from 0.01 kilograms to over 163 kilograms, with diameters spanning 25 millimeters to 900 millimeters, suitable for various industrial sectors. An in-house laboratory and advanced quality control systems ensure dimensional accuracy, material integrity, and consistent performance. At Fersa Bearings, the STREAM0D tapered roller bearing process begins with machining the inner ring raceway on Nova 9. The Aranya system checks dimensions before flange machining on Nova 10. Nova 11 machines the inner diameter with in-process control, ensuring tight tolerances. Temperature is monitored to adjust for dimensional shifts. Inner diameter, conicity, and ovality are controlled for 100% of parts. After honing and washing, rollers are automatically assembled to form the cone. Finally, height and noise levels of all cones are measured to ensure quality compliance. This Sona Comstar Manisar plant is a precision-focused manufacturing facility specializing in electric vehicle EV drivetrain components. The process begins with hot forging of blanks, followed by CNC machining on multi-axis lines for shafts, differential cases, and gears. Gear cutting includes power skeeving and high-speed hobbing, while grinding operations ensure critical tolerances and surface finishes. Each part undergoes ultrasonic washing and dimensional inspection before entering. Differential assemblies are built in climate-controlled zones to prevent contamination, incorporating automated torque testing, QR-coded traceability, and polka yoke systems to eliminate human error. The facility utilizes real-time data capture and closed-loop quality control throughout machining and assembly. Key components are validated via NVH testing, hardness profiling, and CMM inspection. Design verification employs FEA-based stress and deformation analysis to meet stringent EV load conditions. SONA's vertically integrated workflow, from forging to final testing, ensures optimized quality, efficiency, and scalability for global EV. The production of stainless steel cutlery involves a series of precise and highly coordinated processes to ensure quality and durability. It begins with mold processing, followed by the selection of initial stainless steel materials. These materials are cut using stamping and shearing machines, then undergo rolling to achieve the required thickness and shape. After rolling, the materials are trimmed to remove rough edges and excess material. Next, components go through polishing and grinding to refine their surfaces. The products are cleaned, and head welding is carried out to join separate pieces like handles and heads. This is followed by side grinding to smooth the welded seams. The items are then formed using pressing and shaping dies into their final cutlery shapes. Automatic polishing is applied first, followed by manual polishing for detailed finishing. After another round of cleaning, each piece undergoes quality inspection. A laser engraving machine is used to etch logos or designs onto the cutlery, ensuring precision and durability. Finally, the cutlery is packaged carefully, completing the production process for high-quality stainless steel cutlery ready for distribution. The entire workflow ensures strength, hygiene, visual appeal, and long-term performance. Roll threading is a cold-forming process used to produce threads on bolts and fasteners. A reduced diameter steel round bar is forced between two hardened dies, displacing material to form threads without cutting. This method retains material strength and improves thread durability. For instance, a 1-inch bolt is formed from a 0.912-inch rod. The process enhances strength through work hardening and provides smoother threads due to a burnishing effect. Roll threading is cost-efficient, minimizes material waste, and is suitable for long fasteners up to steel bar lengths of 40 feet. Square head machine bolts are manufactured at Portland Bolt using A36 mild steel bars, cut to length with a shear. A semicone point is added for easier installation. Threading is performed via roll threading for efficiency. The square head is hot forged at 2000 degrees Fahrenheit with grade and manufacturer marks stamped. Bolts are cleaned via pickling, caustic soda and sulfuric acid, and hot dip, galvanized in 840 degrees Fahrenheit molten zinc. Excess zinc is spun off in a centrifuge to keep threads clean. Bolts are cooled, inspected, assembled with nuts, boxed, labeled, and shipped. Portland Bolt manages all production in-house for pole line fasteners nationwide. Genga Forging Limited specializes in the precision forging of auto parts, transmission components, bearing components, and railway parts, handling forging capacities ranging from 400 to 450 metric tons per batch. The facility achieves an annual forging output of 10,000 to 20,000 metric tons. The technical process includes advanced forging techniques supported by machining operations such as milling and radial bench drilling to meet exact specifications. Design and process planning are enhanced using CAD/CAM and Pro-E simulation software, enabling precise computer-aided design and analysis. Post-forging treatments like shot blasting and descaling effectively remove pit marks and surface scaling, ensuring high-quality surface finish and durability of forged components suitable for demanding industrial applications. The gear coupling hub teeth cutting process utilizes the Pharaoh CNC gear hobbing machine, renowned for its precision and efficiency. This CNC machine employs gear hobbing, a continuous generating method to accurately cut teeth on the hub coupling. The advanced CNC control ensures consistent tooth profile, pitch, and spacing, critical for optimal gear coupling performance. The machine's capability allows for high-speed machining with minimal manual intervention, enhancing production throughput and repeatability. The resulting gear teeth exhibit excellent surface finish and dimensional accuracy, meeting stringent industry standards for mechanical power transmission applications. The process of punching different-sized flanges is carried out on a CNC drilling machine, combined with a high-pressure water spray system to cool and wash away chips during machining. First, the forged and turned flange is firmly mounted on the machine table. The control system will accurately determine the location of the holes according to specific technical standards. As the drill penetrates the steel, coolant is continuously sprayed to reduce heat, prolong tool life, and ensure the accuracy of the drilled hole. Workers manually remove remaining metal around the defective edge and iron surface, ensuring a clean and accurate surface. After drilling, the hole is edged and the entire flange is checked for size before moving on to the next step. Pharaoh Bearings Italy Santant utilizes certified raw materials and applies controlled heat treatment and protective processes to ensure material integrity and performance. The company specializes in the design, manufacturing, and quality control of radial, thrust, and slewing bearings, with maximum diameters up to 6,000 millimeters. Production follows stringent standards to maintain dimensional accuracy and mechanical properties. Comprehensive inspection protocols verify product conformity. Pharaoh Bearings integrates advanced manufacturing technologies and process controls to deliver precision-engineered bearing components, reflecting Italian manufacturing excellence in heavy-duty and industrial applications. UKB Special Tools 2 delivers customized cutting tool solutions tailored for complex and high-precision machining tasks. Designed specifically for demanding operations such as deep-hole drilling, contour milling, combined boring, or multi-step turning, these tools ensure exceptional geometric accuracy and optimize cycle times. Tool bodies are manufactured from high-strength carbide or steel alloys and coated with advanced wear-resistant layers such as TLN or ALCRN, significantly extending tool life and performance under high-speed or difficult-to-machine material conditions. Insert arrangements, either clamped or brazed, are strategically positioned for optimal cutting angles and chip evacuation. Manufactured using 5-axis CNC grinding and dynamically balanced for high spindle speeds, each tool undergoes stringent inspection using 3D technology to ensure dimensional consistency. UKB's special tools are widely used in aerospace, automotive, and mold-making industries where tight tolerances and high process reliability are critical for serial production. With their precision engineering and custom adaptability, UKB Special Tools 2 represents an advanced tooling solution for modern manufacturing environments. The production of LSAW, longitudinal submerged arc welded, steel pipes, involves a sequential process designed for high precision and efficiency. The process begins with lifting steel plates using a magnet lifter, followed by edge preparation with an edge milling machine to ensure clean, straight edges. These plates are then preformed using a pre-bender machine and aligned via the infeeder machine. Next, the plate is formed into a U-shape and then an O-shape using the JCO press bending machine. A turning transfer car moves the workpiece to the tack welding station for initial joining. Internal welding is completed by the inside welding machine, while any weld bead inside the pipe is removed by the back bead cutting machine. The outer seam is finished by the outside welding machine. The four-way impinging machine adjusts pipe roundness, and an end-facing machine machines pipe ends to required dimensions. Pipes are cleaned with a washing device, inspected with an X-ray test machine, and transferred via a turning conveyor to the varnish coating machine for corrosion protection. Finished pipes exit through the outgoing pipe system. KF Estamperia operates with advanced stamping technology across light, medium, and heavy-duty applications. Its production begins in a dedicated engineering department where high-precision components are designed using CAD, CAE software and validated through prototyping and testing. In-house toolmaking supports efficient die production. Stamping operations are carried out on presses ranging from 40 to 1,000 tons, including automated lines that allow simultaneous tooling for increased output and reduced cost. Welded assemblies are produced in robotic welding cells, ensuring structural accuracy and strength. Optional treatments include chemical coatings and painting. Rigid quality control, including metrology, fatigue, and dimensional testing, ensures compliance with ISO 9001 and IATF 16949 standards, making KF a trusted automotive supplier. The 4-roll Inerca cone bending machine enables precise forming of conical and cylindrical shapes. With synchronized roller control, it ensures uniform pressure distribution, accurate bending, and high repeatability for heavy-duty sheet metal fabrication tasks. The manufacturing and testing of Vinod pressure cookers follows strict Indian standards to ensure quality and safety. It begins with dimensionally accurate stainless steel circles, which are pressed into cooker bodies. These undergo frequent quality checks and impact forming to strengthen their structure. A dry leak test is performed on sample bodies. Fully assembled pressure cookers are filled with water and tested underwater for capacity and leakage. Each unit undergoes a 100% air pressure test. Pressure regulators are tested for performance to confirm pressure buildup and release efficiency. Safety valves are steam tested on 1% of samples to verify they release pressure within specified limits. Gasket release systems are tested under steam pressure for effectiveness, and gaskets undergo 500-hour zero-gravity simulations. Safety and burst pressure tests verify pressure thresholds. Handle joints are fatigue tested using mechanical cycling up to 15,000 times under simulated load. Finally, a hydraulic pressure of 6 kilograms per square centimeter is applied for 1 minute to detect any leaks or deformation, ensuring all products meet safety and durability standards. Investment casting begins with wax injection, where molten wax is injected into a mold to form a precise replica of the desired part. These wax patterns are then deburred and repaired before being assembled into a wax tree. The tree is repeatedly dipped in ceramic slurry and coated with sand to build a ceramic shell. Once the shell hardens, the wax is melted out, leaving a hollow mold. Molten metal is then poured into the shell. After solidification, the shell is broken off, followed by gate cutting to remove excess metal and grinding to achieve the final surface finish. Shandong Wangda is a renowned manufacturer specializing in forging and testing high-quality flanges used in various industries, including oil and gas, petrochemical, and power generation. Their flange forging process begins with carefully selected raw materials, mainly carbon steel, alloy steel, and stainless steel billets, which meet strict chemical composition standards to ensure mechanical strength and corrosion resistance. The forging process at Shandong Wangda uses advanced closed-die forging techniques, in which billets are uniformly heated to an optimum temperature, typically between 1,100 degrees Celsius and 1,250 degrees Celsius. This heating process ensures the plasticity of the material and refines the internal grain structure, enhancing the toughness and durability of the flange. The heated blank is then precisely shaped under a high-pressure forging press to achieve the desired shape. It is then fed into the flange-making machine, which includes a variety of types such as weld neck flanges, slip-on flanges, blind flanges, and threaded flanges. After forging, the flanges undergo a controlled cooling process to reduce internal stresses and improve mechanical properties. Subsequent machining processes bring the flange and bore surfaces to precise dimensional tolerances in accordance with international standards. Shandong Wangda emphasizes rigorous testing and quality control throughout the manufacturing process to verify compliance with design specifications. This comprehensive forging and testing process ensures that Shandong Wangda flanges deliver superior performance, reliability, and safety in demanding industrial applications.